Assalamualaikum. My name is Muhammad Hazim BIC. Today, we will be presenting a study that called Analysis of Radial Output Turbine Design for Supercritical CO2 and Recovery for Radial Input Turbine. So, let's begin with the background, why this is important. This is my group members that called Blue Beetle. So, let's proceed to the background. What about the article? Article is about the study that investigate the design, performance, and mechanical behavior of radial output turbines (ROTs) using supercritical carbon dioxide, efficiency, geometry losses, and operational feasibility to the more commonly used radial inflow turbine, which is RITs. The goal is to determine whether ROTs can offer better performance or design advantage, especially for small-scale and high-temperature power system. Move on to the title and background for this article. Okay. Supercritical carbon dioxide, or SCO2, is gaining attention as working fluid in modern power cycles due to its compact system design, high thermal efficiency, and reduced environmental impact. But however, for the designing turbine for SCO2 is challenging because they operate at very high rotational speeds. Secondly, the design of the turbine is small physical dimension, which create mechanical and efficiency-related issues.
Performance design.
And thirdly is high mechanical stress and agile forces on the turbine. So this research the potential of radial outflow turbines ROTs are less commonly used, but may offer a better performance at lower speed and a wider operating range.
Schematic diagram.
So the main objective is to see whether using ROTs can improve turbine design and efficiency for small scale, high temperature carbon dioxide, supercritical, and power system compared to RITs.
Supercritical carbon dioxide. Yaitu reka bentuk ini merangkum gabungan termodinamik, model kehilangan tenaga, dan analisis tekanan mekanikal untuk menilai presentasi turbin di bawah berbagai keadaan operasi. Meliputi input condition, turbine design codes, geometry, calculation, velocity, changeless performance metric, loss analysis module, stator loss, rotor loss, diff, clearance loss, exit kinetic loss, axial force estimation, infrared stress modeling, output efficiency, stress, axial force, rotation, and speed. Next, metrology, input parameter, loss modeling, turbine geometry and performance design, axial force estimation. This one, Raja schematic system. Ini mari kita lihat aliran kerja melalui raja skematik. Pertama, kita tetapkan keadaan input seperti tekanan masuk, suhu kadar aliran jisim, dan tekanan keluar. Data ini dimasukkan ke dalam kode reka bentuk turbin satu dimensi yang akan mengira geometri turbin, segitiga laju, dan parameter presentasi. Kemudian menurut analisis kehilangan akan mengira kehilangan kecepatan akibat kehilangan stator dan rotor, kehilangan celah ujung, dan kehilangan tenaga kinetik keluar. Seterusnya, daya faksi dianggarkan menggunakan model Wiener cover. Kemudian kita jalankan analisis tegasan impeller berdasarkan formula Osborne. Akhirnya kita peroleh output seperti kecakapan isentropik, tegasan mekanikal, daya faksi, dan kelajuan putaran. Parameter input, bahan kerja karbon dioksida superkritikal, tekanan masuk 200 bar, suhu masuk 600 derajat Celcius, tekanan keluar 78 bar. Kadar aliran jisim 5, 10, 20, dan 40 kg per second. Dua jenis turbin analisis, ROT, turbin aliran keluar radial, RIT, turbin aliran masuk radial. Ini kaidah reka bentuk turbin ROT direka bentuk menggunakan kode satu dimensi sesuai dengan mengambil kira profil laju, radial, dan nisbah kode kepada padang. RIT menggunakan segitiga laju dan hukum kesinambungan aliran berdasarkan pendekatan oleh Royd dan Belge. Ini inflator stress estimation, yaitu pemodelan kehilangan. Untuk ROT digunakan model Soderbeck sesuai untuk bilah dengan nisbah aspek rendah. Untuk RIT digunakan model SM vertikal yang merangkumi kehilangan stator dan rotor, kehilangan celah ujung menggunakan model Johnson, kehilangan kejadian to output matrix. Itu anggaran daya faksi. Daya faksi dikira menggunakan kaedah Munschafer yang mengambil kira aliran keluar, daya pada penutup, daya infus, dan tekanan pada belakang cakera. Ini kode verification itu hasil simulasi, yaitu keputusan yang diperoleh termasuk kecepatan isentropik, geometri bilah dan rotor, kelajuan putaran daya faksi 3 cm. Itu kesimpulannya itu pendekatan ini menyediakan satu rangka kerja lengkap untuk merangka dan menilai presentasi turbin SCO. Dia menggabungkan analisis termodinamik, aerodinamik, dan mekanikal untuk memastikan reka bentuk yang cekap dan boleh dipercayai di bawah berbagai syarat operasi.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Imajini Binti Mawasnan. My meeting number is D0422102226. Today I will present the experimental result of our turbine performance study focused on efficiency, design, implementation, and mechanical behavior across different specific speed. The first graph is turbine efficiency between specific speed. We have found that radial outflow turbine provided high efficiency over 80% of the range of specific speed from 0.1 to 0.7. Maximum efficiency exists around specific speed from 0.5 to 0.6. Since that point in either direction of specific speed, efficiency fall off in both the low speed specific speed due to static loss and the high specific speed due to kinetic outflow loss. Second graph is power output between specific speed. Power output increased with specific speed as well as mass flow rate. Radial outflow turbine blade can provide high power at low speed relative to radial inflow turbine blade, which is benefit for the reduction rotor dynamic issue. The third graph is geometry and blade design. Blade height and outlet radius increase with greater mass flow and smaller specific velocity. Radial outflow turbine blade can vary in height significant by as much as 19 mm, which can create more difficult manufacturing issue, especially when blade height are small. Radial inflow turbine blade, on the other hand, have a smaller amount of radial space. Next graph is rotation speed between specific speed. Rotation speed generally increase with specific speed and decrease with higher mass flow. For example, the higher specific speed with 5 kg per second flow speed exceed 116,000 rpm, while at the low specific speed with 14 kg per second speed drop below 1000 rpm. For turbine loss distribution, there are three loss, namely stator, rotor, and clearance loss. Stator and rotor loss are higher at low mass flow due to clearance effect, especially in radial outflow turbine with very small blade height. In radial inflow turbine tend to have higher axial force, require robust thrust bearing design. Next, we look at the axial force. Radial inflow turbine typically experience higher axial force than radial outflow turbine. In radial outflow turbine, as the specific speed increase, the axial force become more balanced and manageable. This is due to the better distribution of design elements such as force, impact force, and backdisk force. However, when axial force are high, especially in radial inflow turbine, it can lead to mechanical challenge. We need strong thrust bearing to handle the load, and it and this can also reduce the effective power output from the shaft. The last graph is the imperial stress. Both turbines operate safely within the stress limit of the TI6A for both material, with a maximum stress of around 280 megapascal, while below the yielded strength of 330 megapascal at 16 degree. In short, the radial outflow turbine perform excellent at low speed and specific speed, making it suitable for higher efficiency, low speed application. Thank you. For Dr. Yusmadi, thank you for teaching me.
In conclusion, radial outflow turbine can achieve high efficiency across a broader range of specific speed compared to radial inflow turbine. RITs typically reach maximum efficiency at specific speed around 0.5 to 0.6, but their performance drops sharply at a high specific speed. Next, radial outflow turbine is capable to achieve high turbine efficiency at lower rational speed compared to the radial inflow turbines. Other than that, radial inflow turbine experience greater losses caused by large relative depth clearance in the stator and rotor regions. Nevertheless, a specific speed increase axial force in ROTs is significantly reduced and generally remain lower than in RITs. For both turbine, the rotor stresses is acceptable when titanium wheel used. Lastly, replacing RITs with ROTs improves the practicality of the itemized supercritical CO2 system. There are three benefits that can be related to the real-life situation, which are improved energy efficiency, more accurate turbine design, and loss model will lead to better performance CO2 system, increasing energy efficiency in real-world power plants and industrial application. Second, advanced technology integration. Exploring new electric machines like axially laminated and isotropic rotors support the development of more compact, powerful, and reliable energy systems. Lastly, cost reduction and reliability. Understanding and minimizing tip clearance losses and other inefficiencies will reduce maintenance needs and operational costs, leading to longer lasting and more cost-effective systems. From my learning experience in turbomachinery subject, even though it's quite challenging, this subject helped me to understand how turbomachine like turbines and compressor really works in real life.